Hello everybody, this is Yuri again. This time I'd like to show you the one of the main features of 6.9 version 6.9, which is the multigrid option. It has been established already 6.7, 6.8, but now in 6.9 it really has become a standard, mainly due to some new set of boundary conditions which allow the multigrid to work much more efficiently. What it is basically, the idea came from simulating the steel as a part of the solution, because we of course can look at the flow mesh only. So this is like a wire coating example, and this is the flow domain. But of course the flow domain has some extrusion die around, so this is the steel body, and also we have a wire coming through. Now you can say that we can calculate only the flow, but the flow is certainly influenced thermally by the temperature of the wire. Many companies preheat the wire, some companies don't. It is very also important whether the wire has a large heat capacity that is moving fast, or and is big in diameter, or is having a small capacity. So whoever wins really dictates the temperature conditions in the flow and in the wire and die system. So that's why we tend to take these steel meshes into account, and we also need to allow different polymers and different materials in the system. So typically the wire is cuprum, so it's not steel, it's a cuprum wire. And I've used here a steel, but I can certainly put here one more polymer. And then when I want to use the wire as a part of the calculation, you see that's why we've added here a small dialog here, which allows you to choose the particular polymer or material for that grid. So each grid can have its own material. And you also, based on the material, you can see if I choose rigid PVC, I can do flow simulation and heat transfer. But if I use just steel, it finds out that the material is missing flow data, and says you can do only heat transfer in this case. And I'm also able to put here initial temperature, and what is important for the wire is I can set up a grid movement. This grid movement is only in the Z direction, but that allows us to include the convection term which is in the steel, and the convection term can't really be neglected. So we can see that these are quite interesting, and we also have an outer body, and this outer body, when we solve it together, interacts with the flow mesh, and it interacts because the triangles on this body, if I would show you the triangular mesh, you would see that it is exactly as the flow mesh. So to be able to do this, you need to have a conform meshes. So on this surface, the elements need to be exactly the same as these elements on this surface. And what more, you need to put there a special boundary condition, which is interface. You can also see that now we are sort of investigating, and we see two elements there. That's because for my die I've used symmetry, right? So this is the real geometry solved, and I'm only in post-processing or looking at it as a full geometry or as a half of the geometry. And the same I'm doing with the flow mesh. So again, I have flow mesh with symmetry. So this was the real flow domain. And for the wire, I like to show the wire like the whole picture, 360 degrees, but for the solution we of course use only 90 degrees. Now, of course, for the die itself, if you put here a temp variable like pressure, it doesn't have any meaning. Also on the wire, it won't have any meaning. So the only thing what really has a meaning is the temperature, right? So and of course temperature gradients and this kind of things, which densities and so on. Now when you're looking at these three meshes, first, if you want to solve them, you have to always check in their particular solve dialog what is going to be solved. So first I want to solve here flow simulation and heat transfer. My die, I want to solve heat transfer for the wire heat transfer. And now you just multi-select them and then you start the solution. So it's very easy to solve them together. Well, what is the advantage is that I can just say I want now to calculate only the die and the flow mesh. So I ignore the wire very easily and I kick it out from the calculation. Or I can only say, show me what is the result of the flow mesh only without the steel. Now, I can also set up boundary conditions at the top, which will keep the temperatures which were obtained by the previous calculation of the die. So this is very good that we have a multi-grid approach, and we have really 3 different grids. Each one has special polymer, special material, and what more, they can participate on the solution or not. So I can choose whether I do only flow calculation or flow calculation with the outer body, or I include everything together. Now, of course, when I want to see them together, they will use their own limits for the temperature. You see, the limit for temperature is from 150 to 158, but for the flow mesh, it is from 154 to 206. So what we should do probably is really use a limit which would be for all of them the same, and this is the way how to do it. You just say global limits, and now the temperature limits were calculated from all 3 meshes, right? From all 3 grids. So now we see that this is really where we're at. We have a very cold polymer, and this particular example shows that the wire is moving that fast that it really does not heat up at all. Then there is also another boundary condition, and that is that, or another possibility of the program, and that is we can transfer the solution of one flow mesh and take the exit values like temperatures, velocities, and put it to the next one, to put it to the continuation. So you see, this grid is simply a continuation of the previous one, and it has been started by simply we created this grid, and we copied those results of the previous calculation and put it as an input. We see that it's flow rate with temperature, but it has found that the temperature was already initiated, so the calculation did not erase the previous temperatures, right? So we can continue. If we calculate one part of the grid, we can continue from that point and go forward, and that again extends our capabilities. Another thing very nice is that we can do cooling in a calibrator. So this example here is basically a calibrator. Now there is no flow at all. This is really only a situation where we took the flow mesh and the temperatures from the previous calculation, but the solver was having only heat transfer enabled. Also, the calibrator was having only heat transfer, and the wire was having heat transfer, and there was some kind of movement of the wire. I don't remember really the speed of the wire which was used in this calculation. Well, if you want, I can find out by just putting here velocity magnitude, because it should not be. Yeah, it's 5 millimeters per second. This is very slowly moving wire, but so that was initiated like this, right? And this is quite interesting functionality, that we don't have to have a flow calculation. We can do only temperature calculation. If you want to see diffusion, if you want to see how your die heats up based on different heat sources, or what is the heat transfer inside, you can certainly do it. Another possibility is you can calculate with the temperature your flow situation. For example, you can use this particular complex example with the wire and with the body, and then say, okay, that's fine, my heat transfer conditions are found. Now I can just cancel the die and cancel the wire and just do the flow calculation, assuming that these temperature conditions don't change, right? Or there's also another possibility. You can calculate only the flow mesh and the die and the wire, and then you can say, okay, what happens if I start to move the wire faster? So you don't have to recalculate, let's say, the outer body. You can keep the temperature settings from the top as fixed already, found by previous calculation. So this is giving us a big potential, and we would like to use it. Another possibility what I can do is I can do an analysis that I have two meshes, one solved after the other one. So here we use a special boundary condition, which is called in between, right? If I show you the boundary condition, it will be, I can just browse them. And here I have an interface boundary condition, right? Which is this one here, and it's an interface. The interface says that there is basically the same values. So the interface is used between steel and flow meshes, but it's also used between two meshes. So there is no constraint for the polymer to flow across. Okay, so we can solve now this situation independent, this geometry independent. Okay, so what would be the reason? The reason would be that I can solve these two meshes by either together, that I multi-select them, or I can solve them one by one, right? So if I just want to solve the second one, no problem. I just start the solution, and I put here input boundary condition. That's it. If I want to solve the first one, no problem, I can solve it as well, but I need to know the back pressure from the previous one, which I can get very easily. Or I can just multi-select them and start them together. Well, of course, the colors, they look very different. It looks like they are not connected because we have different, again, limits. So I have to look, this is between 0 and 178, and this is between 0 and 263. So let's put here just the same scale, 263, and now we start to see that we have exactly the same colors, because this is really like solved as one flow problem. Okay.